that actually impact the geometry of carbonates during a base level cycle? Well, let's have a look. So at first, let's look at the startup phase. If you imagine that you have an antecedent surface, that antecedent surface could be a former coral reef, or it could be a volcanic basement, it doesn't really matter. Sea level is going up. In white, you have the carbonates. And at first, in the startup phase, the population of the carbonates is fairly small. So they cannot completely fill accommodation. Then in the catch-up phase, the population is just large enough to keep up with sea level. So what they do is they tend to aggregate. So this is a phase of aggradation, and that's typically what you will have during the TST, during the transgressive system tract. You will have aggradation to retrogradation. But then eventually, the rate of carbonate production will exceed the rate of creation of accommodation. And you are in what is known as the Keepup phase. In the Keepup phase, the carbonates keep up with sea level and produce more sediments than accommodation creation, which means that you typically have progradation at the HST of those carbonate systems. And eventually for carbonates, what happens is base level goes down, and immediately those carbonates, the high strength carbonates, are exposed, and you have the creation of that fringing reef here on the side. So in many ways, you can recognize pattern in carbonates that are similar to clastic, but the key is to understand and to integrate the notion of biology in your understanding of how the carbonates are reacting to base level change. And something that is really peculiar to carbonates and unique to carbonates is that you can have a situation where the rate of carbonate production is so low that they do not feel accommodation, and because they are living organisms and because coral need light to grow, they could find themselves in trouble. They could find themselves in a situation where each generation of carbonate is progressively growing in deeper water with less light penetration, and eventually they give up. This leads to what is known as platform drowning. And in the case of platform drowning, you essentially have stop of growth on the platform, and eventually you could have the clastic systems prograding on top of that carbonate systems and covering it completely. And that is something that we see over and over again in a geological record. Platform that otherwise are doing very well, all of a sudden starts to be drowned. And the key to platform drowning is probably ecology again. It's probably something in the system, in the environment, that made carbonates less able to produce, and so that leads eventually to their demise through carbonate drowning. So let's look at an example of drowning in the case of an isolated platform, similar to what you would have in the Bahamas. So if I take here an example of a low stand tract on an isolated platform, we have a small low stand wedge here on the side of that island, and we have a nice sequence boundary. Notice the position of the dominant winds and the dominant currents that push the sediments to the back of this island. So when base level rise in the first instance, we have the creation of this LST followed by an HST. So nothing really too surprising here. Then we have a fully formed HST when base level is high enough. And then, of course, at that point, base level is going to go down, and we have the creation of that LST. Again, this is a fringing reef here on the side, so very small amount of production. But this time, in the next cycle, the ecology of the system has changed. So what do I mean by the ecology of the system has changed? Well, that could mean actually multiple things. It could be, for instance, that we have colder waters that are less favorable to tropical carbonate growth. It could be that we have more nutrient, or it could be that we have more turbid water. The point is, something happens that makes production of carbonate less efficient. So when base level rise, those carbonates no longer can fill the whole accommodation. So they retrograde to the highest point on the island because that's the closest to sea level and the areas where you have the more light penetration. And you can see that now we have a narrower band of carbonate production. It's not the full island that is covered in carbonate. And because these carbonates cannot catch up with sea level, eventually they create ever smaller area of production, all the way to a full drowning sequence where essentially the top of this island now is completely drowned. So drowning unconformities often are characterized by hard ground. The reason they're characterized by hard ground is because the carbonates are in contact with seawater for a long time, and this then promotes the precipitation of cements. That can be carbonate cements, but it can also be phosphatic cements or iron crusts. And that forms the hard ground that then gives to the drowning unconformity its characteristics. Okay, so now you know all you need to know about sequence stratigraphy. And in the next lecture, we will start to look at rhythmic sequences and what control the stacking pattern vertically of these sequences, including cyclostratigraphy.